In this video, we're going to discuss chemical equations. Now, in one of the first videos in the course, I described chemical reactions as just a rearrangement of molecules to form some new molecule or molecules, right? And chemical equations are a way for us to be able to communicate that rearrangement of a chemical reaction. Right. So what does a standard chemical equation look like? Well, let's try to write a chemical equation for this process that we see here. Right. So we have hydrogen plus chlorine making hydrochloric acid. Right. So if we were to write this out as a chemical equation, we might put H2 plus Cl2 forms HCl. Now, there's a few details that I'm skipping over right now, but I just want to get the basics of the anatomy of a chemical equation kind of down first, right? So what makes up this chemical equation? Well, there's some stuff on the left side of the arrow and some stuff on the right side of the arrow. The stuff on the left side of the arrow here, this is what we call reactants. Right, so hydrogen and chlorine are going to be your reactants, right? So during a chemical reaction, the reactants are the compounds that are consumed during a chemical reaction, right? So these guys are consumed during a chemical reaction. Right, you could have one compound on this side, you could have two, you could have multiple compounds on this side, right? This is just telling you everything that's involved in a chemical reaction, right? Everything that you're starting with, everything that's going to be consumed during the chemical reaction, right? And then we have this arrow here, right? This is what we call the reaction arrow. And the reaction arrow serves a very simple and consistent job of basically just telling us that a chemical reaction is happening, right? So you're saying this is everything that I'm starting with. A reaction happens, and then the stuff on the right, those are the products. That's what's formed during the chemical reaction, right? So these are the compounds that are formed during a chemical reaction. Right, so this is the basic skeleton of any chemical equation, right? You have some reactants, right, which will have a plus sign to denote each separate reactant. These are going to be consumed during a chemical reaction. The arrow tells you that a chemical reaction occurs, and then the stuff on the right-hand side is the products that are formed during the chemical reaction. Now, you may notice that there's something a little weird about this chemical equation that I've written here. If you took chemistry in high school, you probably remember balancing chemical equations, and you might have immediately noticed that this equation is not balanced. But first, I want to give you the why. Why do we have to balance chemical equations? Well, think back to the first fundamental law of chemistry that we discussed. That first fundamental law was the law of conservation of mass. So what that law said is that mass can neither be created nor destroyed. Well, let's look at what we're saying here, right? So I've put this figure here to kind of show you what this would look like looking at the ball and stick models of the molecules, right? So the hydrogen here, right, we're starting with two hydrogen atoms in the reactants, right? And we're starting with two chlorine atoms in the reactants. But then we only form one molecule of HCl. If this was true, then what happened to the other hydrogen and the other chlorine molecule? This would imply that those molecules were simply destroyed. That would fly in the face of the first fundamental law of chemistry, right? So that's why we can't have this unbalanced chemical equation. In general, whatever you have on the reactant side, all of those atoms have to be accounted for on the product side, or else you're disobeying the law of conservation of mass. So how do we do this? How do we make a better representation that fits with the law of conservation of mass? Well, what we do is add something called stoichiometric coefficients, right? So let me write that down. So stoichiometric coefficients. And these are going to be integers that you would basically multiply the composition of your molecule by in an attempt to try to balance the equation in order to fit with the law of conservation of mass. So in this case, we have 2 hydrogens here, 2 chlorines here, right? If I just multiply the HCl by 2, then I have a balanced equation. So what I can do is put a 2 out front here, right? This is our stoichiometric coefficient, right? That 2 is going to balance our chemical equation. Now on the reactant side, we have 2 hydrogens, we have 2 chlorines, and now if we include this stoichiometric coefficient, now we have 2 hydrogens and 2 chlorines on the product side. So what does that look like as far as the ball and stick model goes? Now this looks like a better representation of what's actually happening and what's actually consistent with the law of conservation of mass, right? So we have 2 hydrogens here, 2 hydrogens here, 2 chlorines here. That's going to form 2 molecules of HCl, right? So now we've obeyed the law of conservation of mass. No atoms were created or destroyed. So now we have a good representation of this reaction. Now, another thing that chemical reactions typically, or chemical equations typically convey, is the phase that each compound is in. So what do I mean by that? By phase, I'm talking about solid, liquid, gas, right? Sometimes there are multiple different phases involved in a chemical reaction. So one example would be the combustion of ethanol, right? So if we take ethanol, right? So we have C2H5OH, right? This guy is going to be a liquid when it goes through combustion, or it can combust as a liquid. So the way that we denote that is by putting something in parentheses after each compound that denotes its phase. For a liquid, we use L, and I like to use a cursive L just so that it's distinguished from a 1. But each phase has its own letter. So the L is for liquid, G is for gas, S is for solid, and we also denote if something is in aqueous solution. Now we'll talk more about aqueous solutions later on in the course, but basically it's anything that's dissolved in water. So we use AQ to denote an aqueous solution, right? So these 4 labels are typically added to chemical equations, not always, but when you really want to be specific about what phases each compound is in, you add these identifiers to the chemical equation. So we can finish out this combustion reaction. I'm going to go ahead and have it balanced. So in order to combust, ethanol is going to react with excess oxygen as a gas, and that's going to produce carbon dioxide gas and H2O gas, so water vapor, right? And so this is the combustion of ethanol with each of the compounds labeled appropriately as in which phase would be involved in the process, right? So basically, as far as a final summary overview, chemical equations are just the language with which we speak how chemical reactions occur, right? Just like mathematical equations convey, the math that's at play, these chemical equations convey the chemistry that's at play. So it's a way for us to communicate how these atoms are rearranging, right? The before and after snapshot of the rearrangement of atoms throughout the course of a chemical reaction.